Hi. Imagine being the perfect freedom and all the resources to design a data pipeline from scratch. How would you do? What would you do? So I'm going to talk about how we created our data pipeline and what decisions we had to make while building it. I will start a very brief introduction, and I'm going to move on to why we needed it. So my name is Gabor. I received my master's from the University of Oxford. I worked for a systematic hedge fund for a couple of years before joining Optiver's quant research teams. My main duties are building systematic trading strategies and also building this pipeline. I sit amongst data scientists, data engineers, fellow researchers and traders, and together we form this constant feedback loop while trying to improve our decision making. We are highly data driven, so quantitative methods, predictions are at the forefront of what we do. Optiver has been around for 36 years. And why is data important for us? So we started with a single trader in the Amsterdam's options exchange. And this is where traders had to use hand gestures and shout to get information across. Traders were monitoring with their eyes and ears just to see like what trades just happened, how to react to them. They were very good at maths, mental arithmetics, to see like based on what positions they had, what positions they want to get into. We traded only a couple of instruments back then, and most of the things were not automated. So if you wanted to expand, you had to hire smart math wizards, train them up on how trading is done, put them into this trading pit, and this was a very slow and gradual process. Over the years, things have changed. Electronic exchanges introduced a new way of trading, which brought a new set of challenges, but also the opportunities to automate things. On an average day, we make around 3 million trades on over 100,000 instruments, and all of this with just maybe 150 traders. So the scaling to more instruments is now happening on how fast you can make decisions. And so we are enabling our traders to make better decisions faster by this automation. The main reason, I was wondering if you could estimate the number of data we get every minute. Anyone? Okay, so we are connected to over 50 exchanges, and this is raw data, so this is just price time series. It's about 100 gigabytes. So for a normal human with a reading speed of 250 words per minute, it would take around 126 years to process this data that we receive in a minute. So clearly, automation was necessary for us to progress forward. The data requirements for automation and predictive analysis with complex models required some advancements also to our data pipelining. So here comes the why. Why question? Why build a data pipeline for ourselves? Our previous data pipeline started to become outdated. We were trying to scale up to more underlyings, meaning more products that we are trading, like Tesla stock or other options, and with more and more complex models, because we wanted to achieve better prediction. So we started timing out on database queries. The number of calls that we sent to databases also sometimes brought down replication servers. So we were in constant need of optimizing and re-optimizing our code just in order to maintain the update frequency of the predictions that we had to produce. So one of our trading teams alone needs 5,000 plus predictions in every minute. So this is kind of the scale that we are talking about here. So what we needed was something that was accessible for a wide group of people. We wanted to enable our traders who are less tech savvy to be able to write scripts just as well as data analysts, data engineers, and other quants. We needed something that was able to produce results that matched the live, so making it in production, and the backtest performances. we also needed something that was scalable to large computational graphs. Some of our production graphs have over 10,000 edges. And when we were looking into existing solutions, we realized that there is no one thing fits all. It's not easy to find a solution readily available because the design choices are very much influenced by your use cases. So we looked at a lot of different tools and we picked ideas, but we could not just overwrite one of them. We had to go from the ground up because it would have taken us maybe even longer time to rebuild one of the existing solutions. At times, it could be quite difficult to sell a product like this to existing teams that are already working with a different pipeline. And yeah, it's one of those things that, oh, sorry, I'm too busy. I don't know. Please, next time I will have a look at it. But this tool that we have built has made big enough waves that currently our main dev is in Chicago discussing how we can make it into a global tool. So yeah, because we designed it ourselves, we made the trade-offs between the latency needs we had, the consistency between the code and the logic and the data. So how it works and why it works. We have designed it entirely in Python. So each script we write uses a set of nodes with relational mapping between them, and this forms a DAG. So this is a directed acyclic graph, quite common in the industry. We specify our features as subgraphs and have an elimination of common nodes. So you have the subgraph elimination to not having to recompute something that you've already done. Each node is part of the main graph and has an understanding of what it relies on. So it will only compute once all its upstream nodes have computed. We use an event loop, async, and multiprocessing to take care of I/O and heavy computational nodes. So for those of you, like if you can't really see it really well, but there is some writing in these nodes. These are the hashes that we produce for them. And I will come back to it when I'm talking about the caches of these. And secondly, this is a simplified version of some of the large node systems that we have. But because we have over 10,000 edges, it just would look like a mess. The upstream nodes, the orange-colored ones, are the raw data input nodes. These usually read data from either a historical database or a bus, in our case, a Redis server. And they could be specified as easily as any other node. These are our connection to the real world and the data. The blue nodes are derived nodes. They usually have at least one upstream node. And this could be anything from simple transformations, like a log transformation of a feature, or as complex as a complete regression algorithm. Could be any machine learning algorithm you can imagine. And the final node at the bottom here is what we call the sink. Could be the root, but I don't want to get into terminology issues because you can call either this a leaf or the top a leaf. So yeah, let's just not get into it. So this is the sink, and usually this is going to be what we produce, and this can be stored in a live database. Each node that we construct produces an infinite time series. So they are endless. And you can pull them forward in time. So if you run a script live, you can say, get me as of this time, and it will signal all the way upstream, and it will move everything forward to that timestamp. Because we can have different resolution nodes, you can have them at milliseconds, seconds, minutes, or even like a couple of days frequencies. We specify them as calendars. And when these different frequency nodes have to interact, we decided that we need to use something special, an upsampling or downsampling for them, And this interaction happens at one of these child nodes. We also put in a hybrid caching system, which I will come back to a little bit later. And so why does it work? And why it works for us? It's been designed from the ground up with our needs in mind, which means looking at very short-term predictions on financial time series. It allows us to write scripts very easily, no need to write low-level C code, so it's very accessible to people. And it's fast enough for our human latency needs, which means on a seconds to 10 seconds level, I'm able to produce predictions from complex models. And overall, like moving on from our old pipeline to this new one, it has allowed us to make predictions from raw data to predictions from a couple of minutes down to sub 10 seconds. This was one of the larger projects that we have worked on. And because of this, we had a lot of going back and forth between the business owners, developers, traders, just to understand their needs. And these talks ended up with a lot of questions, as you can imagine. How do you do this? Why would you do that? How can we design it better? And so what I wanted to talk today is the general theme of these questions and the answers that we come up for them. So could you think of a couple of questions that you would have if you had to design a data pipeline yourself? I will go through a couple of semantic ones. So the first couple are design related, and they relate to why you should write code that is used by both the live and the historical. How do you speed up the research to production cycle? And how do you ensure that what you have run in your backtests is going to be the same performance in live environments, so in your production? The second group is how fast does it need to be? Do we need something as low latency as in nanoseconds, or do we want something that gives us some convenience to be able to use Python as the backend? Next question was data that is arriving asynchronously. What do we do with this? How can we deal with it? And the final set of questions are all related to resource management and caching. So how do you reduce the number of queries you have to make? How can you speed up the day-to-day research? And what do you do with the stateful nodes? So, should you write code that is used by both live and historical pipelines? We are going to tackle this from both a general and a research perspective. Let me start with a quick story. So, a couple of months ago, I had to move our Python 3.6 built library into Python 3.9. And I thought everything was going fine until we hit production. We had a lot of bugs that were not covered by unit tests. And you only realize it when you actually have to upgrade your packages that something under the hood has changed. So obviously, this is a Python to Python conversion, and only Python libraries being updated. But still, some things can go wrong. Now imagine the same thing happening if you are doing it between Python and a different low-level language that doesn't have any of your packages. So it's not trivial. For our research to production perspective, writing code once enabled us to replicate live behavior in the backtesting, which boosted confidence in our strategies. And this way also we avoided any logic translation bugs inherent in this moving from one package to the next, etc. So writing code once enabled us to do all of this. And also with writing once, you don't have any of this research to production cycle. It's practically the same. You write it once, you use it in both environments. So the research and the production are identical. You don't have any mismatches. There is, however, also an opportunity to reflect on the other side of this coin, because writing separate code for research and production can also be a viable opportunity for something that needs to be more speedy that Python can offer. So there are definitely use cases where you want to have this flexibility which enables you to write performant code for your production purposes, but you want your researchers to be surrounded with the packages that they are all familiar with. For us, it just wasn't an option. We need the live and the backtest frameworks to match perfectly, otherwise you don't know what trades you are making, and it's just very dangerous. So moving on, how fast does it need to be? We at Optiver, we are market makers, which usually people will associate with high-frequency trading and co-locations, but this is not what we are going to talk about today. What I'm referring to is the human latency, the seconds latency. And for example, this could be dashboarding applications or non-event-driven predictions. So a quick question would be, would you rather spend your time rebuilding the Python data stack on the right from scratch, right? Or spend your time on tools that are not so readily available or really far from your potential optimal use cases? When we asked our researchers, the answer was unanimous. Please let me use all these libraries which have thousands of devs backing them. I want to be able to use this nice PyData stack. This doesn't mean that you can write bad code. You still need to write performant code. And so we do whatever it takes to speed up the core of the library, the core of this data pipeline. And we utilize a lot of these nice packages like Numba, Cython. Sometimes we have to wrap some C code just to enable us to do something faster. We try and vectorize everything. So NumPy, one of our closest friends. With the raw data nodes in place, you also want to use something like async, so you don't have I/O blocking issues. You also want to use multiprocessing, so some of your computationally intensive nodes don't hog all the resources and block your computational graph. Okay. What trade-offs do we make when the input data arrives asynchronously? In some traditional ETL-like frameworks, so Jenkins or crontab, you might query a table at a certain time, let's say at time X, and you make the assumption that all the data is up to date by that time. Okay, this assumption might work for some applications, but I will give you an example where it clearly breaks. So let's assume that you are trading two stocks, and these stocks are very codependent, so they move up and down together. And then when they really move apart, like one of them prints a much larger number than the other, okay, you sell the better performing one and buy the lower performing one and bet on the convergence of the two. So this is a very basic spread trading strategy. And suppose everything ticks at the same rate. You have updates every second or every 20 seconds. Doesn't really matter for this. But for some reason, your database connection or some raw market link goes down, and for stock B, you're not receiving data for a minute. And in this minute, markets are very busy, probably why your market link went down. And so it just happens that stock A has printed a large value. And since you assume that the data is still correct, you have this forward fill value of nothing happening to B. So now you're selling A and buying B, betting on the convergence. All good, right? So now suppose that B actually comes back alive, the market link survived, and the data shows that actually B printed a much larger value. So the trade you should have made was selling B and not A. You're on the wrong side of the trade. So this is clearly a completely hypothetical scenario, but it demonstrates the problem that we might be facing in finance when the data is arriving asynchronously. It doesn't really need to be that a market link or whatever raw data is not arriving on time. It also could be that you make a query through your database or one of your computational nodes is not running on time. So how do we deal with this? What do we do? we say we are rather still than wrong. So we wait until the latest data is available for all the underlyings. And this just made sense to us. Maybe for other purposes, it doesn't make sense. So in our deck design, how we ensure this is that once a node at the bottom is requested to produce a new value, it goes all the way upstream. And on the raw data, we have this blocking. And until the raw data has arrived, you can't compute the downstream. So this is a very easy way of doing it. Now I have to mention that you obviously will have nodes with different update frequencies. So you can have nodes that are regressions that you don't want to retrain every minute. You might have them update every week. So what do you do if you want to predict it every 10 seconds? Are you going to block now for a whole week just because, oh, the regression is not up to date, please wait, right? You wouldn't do it. So this is where this up and down sampling has to happen. You can have nodes that are at much higher frequency updated, like at milliseconds, and you can combine them with daily data that you just need to build a logic around it. So how do we deal with resource management? The simple DAG represents a hypothetical dependency graph. And at the top, we have the raw data, the upstream inputs to where we are fetching market data, let's say prices and trades that just happened. The middle layer is going to be some transformations on this data and could be some regression or a backtester framework. And so on the first run, let's say this is a very, very simplified version of a backtester. This is how a backtester looks like. So I fetch all my data. It could be a lot of data. It could be gigabytes of queries coming through. Then I have some computational nodes that have to compute some very stateful outputs, like position vectors that change over time. And finally is my backtest results, which is going to give me how good performing is my strategy. Now, I forgot to do something. One of my nodes had the wrong logic. I need to modify something. Or I'm just running multiple of these strategies, and I just don't have the resources to run them parallel. So what can I do? Obviously, you don't want to run it parallel either, because you are just going to download the data all over the place. So what do? Well, we didn't cache anything. So I have to go back, download the raw data, compute the states, produce. Not ideal. So what I do, I just replicated it, and I add node-agnostic caching. So what does that mean? So most of these nodes are loading data from databases and producing some outputs. And these outputs are usually something nice like data frames. So you can store them down in HDF or whatever tickles your pickle. And you can go all the way down and get the root node. And now the second run, I'm way faster because I don't have to load the data, because I can just use these node-agnostic caches. I make the assumption that the raw data didn't change, but I can literally reach my end results instead of hours in probably a couple of minutes. I deliberately left out a couple of edges without the green, and these are potentially the nodes where you don't want to cache. And there could be two reasons for this. The first main reason is you are using them and you are modifying the logic inside. So you're running separate, different, maybe a grid search, and it just doesn't make sense because whatever you're going to cache down is never going to be used again. Or you are using something that is super fast to compute, and loading it from the data is going to be just slower than actually doing it this way. So overall, no caching, not an option. You have to do some kind of caching for us. And this node-agnostic caching seems to work. It's perfect, right? Well, not quite. Moving on from the historical testing to real-time computations, so production, there are certain things that won't work. Running the scripts by starting them up, making them compute, publish, and then exit, works really well for the backtesting and for lightweight scripts. However, for others, this cycle that you have to keep like waking them up, well, not waking them up, starting them up again, it just doesn't work. The startup cost could be expensive, and the computation of some of the states could be just prohibitive for your use cases. Even if the update frequency is just like 10 seconds, the state computation alone can be too slow. Like what I mentioned earlier, the position vectors, they are really path dependent, and that means that you might at times have to go through a month or a couple of months of data, simulate through it, just to land on the same timestamp, on the previous timestamp at the same position as you had in the previous run. So these are very expensive computations, and you don't want to deal with this. So in summary, the node agnostic caching kind of works because it helps loading all that historical data. It's already cached for us, and you can just append to it. It's nice. But for light scripts, there is still something missing, the state itself. So does this mean that you have to cache the state of each node? I think we have found like a nice quick win, and this is staying alive. So what does this mean? You have a cycle that is very, very close to our previous one, but instead of exiting, so you make the publish, you publish your prediction or whatever your output is, you go into sleep, and you have something that orchestrates a wake up at certain times of your script. And so how does this help us? This allows us to keep state in memory. So it speeds up this whole cycle because you don't have to do any of this computation anymore. When my event loop says, oh, please wake up now, fetch me the recent data, pull everything forward in time, all I have to do is very small incremental computation. And this allows us to really make predictions at sub 10 seconds for quite complex models. Now, obviously, things can go wrong. What if the script crashes? Or I'm running this during the day, but I realize that there is a bug. I need to redeploy something. So in these cases, well, we have fallen short of this promise of this in-memory cache. And what we need to do in these cases is really node-specific caching. And there are multiple different ways of doing this. You can put them on a separate server. You can keep them locally, depending on how reusable these state caches are. But once you've done this, once you have put all of these node-agnostic caching, running them live, and these state caches, there's not much that can slow you down. So in summary, we don't have we need the node-agnostic caching for the historical testing, and the in-memory caching can speed up a lot. And the state-specific caches of the nodes can actually help you bring up this cycle much quicker. So in summary, bringing it all together, going back to what we really needed and how we have achieved this. So we wanted an easy to use by a large variety of backgrounds. We wanted traders to use it as easily as our quant devs. Written in Python for accessibility, and also the convenience. You have all the pipelines, you have all the PyData stack available to you. It produces perfect match because, yeah, you have written it once. And it's scalable to large computational graphs. So what we have learned is writing once and using everywhere. It has really provided us with this nice framework, so you don't have to worry about your backtest mismatching your production. You don't have logic translation bugs anymore. The research to production cycle speeds up massively. We used to write stuff in Python, then translate it into some low-level code. It takes some time. It takes developer effort. Trading part of speed for convenience. It has allowed us this easy-to-use yet enough for our human latency need framework. And so we managed to eliminate a lot of duplicate efforts from different teams trying to write their own features all the time. Everything is centralized. Everything is easy to use. We gave access to pretty much anyone who knows basic scripting. Being stale rather than wrong, it has simplified our trading logic. You don't have to write separate scripts or what happens if X is not updated. What happens if Y is not updated? You might have dispersion models compromising of multiple products, and these dependencies can be very, very cumbersome. So it just simplified our complete logic. And staying alive, aka the hybrid caching, has allowed us to speed up our predictions from a couple of minutes to sub 10 seconds for even super complex models, and we can now do it for thousands of underlyings at the same time. So we can do this and much bigger. Thank you, and that's it.
Thank you, Gabor. Is there any question from the audience? Oh, many questions. Let's start here, then I walk back.
Hi, thanks for that. One of your reasons for data arriving asynchronously was because like a node takes a long time to complete. I can sort of see a scenario where if is it sync node, the green ones? The ones?
Yeah.
If it refuses to produce an output because an upper node is taking a long time to complete, like you can see a scenario where you end up not producing the outputs. Like what do you have a mechanism for that, or has it occurred? Or stuff like that?
What you're asking is essentially, so what do you do when actually one of your nodes is slow and it's not updating as it should be? It's annoying, right? So this is where you go back to the drawing board. Okay, maybe I need to re-optimize some of these nodes, because it's a different perspective. Being stale rather than wrong, it means that, okay, I might at some times have to slow down and produce an output at a later state because I just can't feasibly produce you something that is completely correct. And this is clearly a trade-off. For some use cases, this is inefficient. You want React as soon as one of your inputs has arrived. And for our cases, most of the time, this wasn't the case. We wanted something to be completely correct.
Hi, thank you for the talk. I would like to ask if the quants need to be aware of the structure or the API of the computing system, especially if there is any kind of algorithmic restrictions on what they can implement, depending on a batch or an online algorithm. We know that not every batch algorithm can be turned into an online algorithm. How do they resolve this?
Yeah, so it's pretty much building blocks. So the API is very free to use. It's essentially, we have all the raw data available, and there are some nodes that are more complex than others. Some of these we require devs to build, and then we can give these to the researchers. So it's not a streamlined process for everything, but for most easy to use tasks, when you ask a trader, oh, I have an idea, but I don't have the time to implement it for you. Okay, this is where I can teach them. Okay, look, this is Python. You can specify your input nodes. These are the raw data nodes. You specify what features you want. You specify what type of machine learning algorithm you want, and then I can output you a prediction. This could be very simple as well. You don't need predictions. You could make just some transformations from data and construct something for your dashboarding, so you can see some meaningful features that you obviously couldn't do before. So we can talk later as well. It's not always straightforward.
Hi, thanks for the talk. I just had two questions. The first one's related to the live versus backtesting alignment.
Mm-hmm.
So it sounds like the pipeline and the kind of buying, selling decision code are both written in Python.
Mm-hmm.
What kind of implications does that have on latency and execution and that kind of thing? Like, how can you ensure that the live and the backtest are the same when, presumably in the live setting, the latency matters a lot?
Indeed. So obviously what I was presenting here is one of the many pipelines that we have at Optiver. When it's really latency sensitive, we have a much lower level library. Right. For our human latency needs, it means that you have the time usually to be able to react on top of it. So I can give you an example. So if you're trading as frequently and you're turning over only once an hour, does it really matter that you have executed it at a millisecond level, or does it really matter whether you have done it in a first couple of minutes? There might be small backtest and live mismatches because of the execution of the trades, but that doesn't mean that you have complete disparity between them. The logic is the same. If you automate the execution, it should be the same, but there's clearly this assumption that you make in backtest that you can run at certain frequencies and you have perfect hedges at the right time, etc.
Okay, that makes sense. Yeah, the second question was just thinking about the caching system. Is the caching system kind of like keyed by 2 time dimensions, kind of like an as of and seen from? Like what happens?
Yeah, I forgot to mention this, but one of the key inputs to this was, okay, when do we break the cache hash? And essentially we come down to actually looking at the whole logic of the node, and we hash that. But obviously the node itself doesn't really know about its parents changing. So we actually hash all the parents all the way up, and everything is hashed together. And then whatever hash we have, we store with that. And if something is changing upstream, the whole dependency graph from that node downstream will have to recompute. So this could happen like I modified one of my hyperparameters, and because of that my regression changes, because of that some backtest inputs change. So everything downstream from there has to recompute. So this is where, okay, there could be one more iteration on top of this, which is when you're looking at raw data changing under your feet. Usually you wouldn't assume that historical data will not change. But sometimes somebody inputted the wrong data, you get the modification, now you reload it, and you get a different output. So if you don't break the cache on that, you're going to get different results later on. So there is a trade-off. You can then specify that please recompute this node. And if you recompute it, then everything downstream will recompute as well.
Okay, cool. Thanks.
Any more questions? No? Then let's think.
There was one more.
Sorry, didn't see.
I understand that probably most of your nodes and the data that you work with are time series, right?
Yes.
Are there any nodes that have non-time series Z or numerical data?
There are, but I can't really talk about them.
Okay. Okay, but is it just, I guess, categorical, some sort of category?
Could be. Sorry. Yeah.
Okay. So let's thank Gabor again for the talk.